Hello and welcome to the Quiet Cosmos. Before we begin our journey tonight, please take a moment to like the video and subscribe to the channel if you enjoy calm explorations of space and science. It truly helps the channel grow and allows more people to discover these quiet journeys through the universe. And if you feel like sharing, let me know where you're watching or listening from tonight. Are you listening from a quiet city apartment, a small town under a dark sky, or perhaps somewhere where the stars are just beginning to appear outside your window? It's a fitting question, because wherever you are on Earth right now, you're sitting in a very specific place in a very vast universe. A universe that, according to our best scientific understanding, began nearly 13.8 billion years ago. Tonight, we're going to explore one of the biggest scientific ideas ever proposed, the Big Bang. You've probably heard the phrase many times before. It appears in textbooks, documentaries, and popular science discussions. It's often described as the moment the universe began, a sudden birth of space, time, matter, and energy. But here's the quiet mystery that cosmologists continue to explore. Is the Big Bang theory actually correct? Not in the sense of belief, but in the scientific sense. Does the evidence truly support it? How strong is the case? And are there other possibilities scientists are still considering? Because the Big Bang, despite its familiar name, is not simply a story about a cosmic explosion. It's a carefully constructed scientific model, built from decades of observations, equations, telescopes, and experiments. A model that attempts to describe how the universe evolved from an incredibly hot, dense state into the vast cosmic landscape we see today. Over the past century, astronomers have discovered clues scattered across the cosmos, galaxies moving away from each other, ancient light left over from the early universe, patterns written across the sky that seem to preserve the fingerprints of cosmic history. Together, these discoveries form the foundation of modern cosmology. But science is rarely simple. Even as the Big Bang model has grown stronger, new questions have emerged. Strange mysteries about dark matter, puzzling forces like dark energy, subtle tensions in measurements of the universe's expansion. And then there are the deeper theoretical possibilities, ideas about cosmic inflation, quantum universes, multiverses, and even repeating cosmic cycles. Some of these ideas reinforce the Big Bang, others challenge parts of it, and some suggest that what we call the Big Bang might not have been the true beginning at all. So tonight, in this calm journey through cosmology, we'll gently trace the story of how scientists arrived at the Big Bang theory, examine the evidence that supports it, and explore the fascinating ideas that continue to test its limits. From the first hints that the universe might be expanding, to the faint glow of ancient radiation still filling space today, to the strange theoretical frontiers where physics and philosophy begin to overlap. This is not just a story about the beginning of the universe. It's a story about how humans try to understand something unimaginably large, using nothing more than careful observation, mathematics, and curiosity. So settle in, relax, and let your mind drift outward for a while. Because tonight, we're asking one of the most profound questions science has ever attempted to answer. Is the Big Bang theory correct? And to explore that question, we have to begin by rewinding the universe itself. For most of human history, the night sky has raised a quiet but persistent question. Where did all of this come from? Every star, every galaxy, every atom in the ground beneath our feet. All of it belongs to a universe that clearly exists. But the deeper mystery is not simply what the universe contains. The deeper mystery is whether it has always existed, or whether it began at some point in the distant past. Modern cosmology approaches this question using telescopes, mathematics, and physical theory. And at the center of that effort stands one of the most famous ideas in all of science, the Big Bang theory. You've probably heard the phrase many times before. It appears in textbooks, documentaries, and conversations about space. The idea is often summarized very simply. According to this model, the universe began in an extremely hot and dense state, roughly 13.8 billion years ago, and has been expanding ever since. But even though the phrase Big Bang sounds dramatic, the theory itself is not a story about an explosion in space. Instead, it is a model that attempts to describe the expansion of space-time itself. In this picture, space is not a static stage where galaxies simply move around like drifting ships. Space itself stretches and grows, carrying galaxies along with it as the universe evolves. The Big Bang Theory therefore tries to answer two connected questions at once. First, how did the universe reach the enormous size and structure we observe today? And second, what were the conditions of the universe in its earliest moments? To understand how scientists arrived at this idea, it helps to look back at how earlier civilizations imagined the universe. Long before telescopes existed, philosophers attempted to explain the cosmos using observation, logic, and speculation. In ancient Greece, one early thinker named Anaximander proposed that the universe might have emerged from something he called the apeiron, a boundless and indefinite source from which all things arise. While this concept was philosophical rather than scientific, it showed an early attempt to imagine a cosmos that had a beginning and an underlying origin. Several centuries later, Aristotle presented a very different vision of the universe. Aristotle believed the cosmos was eternal and unchanging. In his model, the heavens were made of perfect spheres that rotated endlessly around the Earth. The stars were fixed, the celestial motions were orderly, and the universe had no beginning and no end. This idea of an eternal cosmos remained influential for many centuries. Even when scientific thinking began to replace ancient philosophy, the assumption that the universe had always existed continued to feel natural. The English mathematician and physicist Isaac Newton, whose work in the late 1700s transformed the understanding of motion and gravity, imagined a universe filled with countless stars extending infinitely in every direction. Newton's law of gravity explained how objects attract one another through mass. In simple terms, the force between two objects depends on their masses and the distance between them. In modern notation, the relationship is expressed as force equals the gravitational constant multiplied by the product of two masses divided by the square of the distance between them. This law worked beautifully for planets, moons, and falling apples. But when Newton applied his ideas to the universe as a whole, he encountered a puzzle. If gravity pulls matter together, why had the entire universe not collapsed into one enormous clump of stars? One way around this problem was to assume the universe was infinitely large, with stars distributed evenly in all directions. In such a scenario, gravitational pulls might balance out on average. For many scientists in the 1800s and early 1900s, the universe was therefore imagined as both eternal and static. It simply existed, unchanging on the largest scales. The idea that the universe itself could evolve over time had not yet taken hold. That changed dramatically in the early 20th century, when physics underwent a profound transformation. In 1915, the German physicist Albert Einstein introduced his theory of general relativity. Rather than describing gravity as a force acting across empty space, Einstein proposed that gravity arises from the curvature of space-time itself. Mass and energy bend space-time, and objects move along the curves created by that bending. When Einstein applied his equations to the universe as a whole, he discovered something surprising. The mathematics suggested that the universe could not remain perfectly static. The equations naturally described universes that either expand or contract. Einstein found this result troubling. At the time, there was no observational evidence that the universe was changing in size. To preserve the idea of a stable cosmos, he introduced an additional term into his equations known as the cosmological constant. This term acted as a kind of repulsive influence that balanced the attractive pull of gravity, allowing the universe to remain static. But other scientists soon began exploring the equations of general relativity more freely. The Russian physicist Alexander Friedmann showed in the early 1920s that Einstein's equations allowed expanding universes without any need for a cosmological constant. Around the same time, the Belgian priest and physicist Georges Lemaitre independently reached similar conclusions. Lemaitre went further, proposing that if the universe is expanding today, then in the distant past it must have been smaller, denser, and hotter. He even suggested that the entire universe might have originated from what he called a primeval atom, an unimaginably compact state from which space and matter emerged. These ideas were bold, and at first they remained largely theoretical. There was still no direct observational evidence that the universe was expanding, but that evidence would soon appear. Over the coming decades, astronomers would discover that distant galaxies are moving away from one another, that ancient radiation still fills the universe as a relic of an earlier era, and that the chemical composition of matter across the cosmos carries the fingerprints of extreme conditions in the distant past. Piece by piece, these discoveries built the framework of modern cosmology. The Big Bang Theory emerged not from a single moment of inspiration, but from the gradual convergence of mathematics, observation, and physical reasoning. Still, science rarely settles questions permanently. Even today, cosmologists continue to test the Big Bang model against new data, new observations, and new theoretical possibilities. Some ideas strengthen the theory, others challenge parts of it, and a few suggest that what we call the Big Bang might represent only one chapter in a much larger cosmic story. To understand whether the Big Bang truly describes the origin of the universe, we must examine the evidence carefully. And that evidence begins with one of the most remarkable discoveries in the history of astronomy, the realization that the universe itself is expanding. For a very long time, the universe was assumed to be calm, stable, and eternal. The stars appeared fixed in their patterns, night after night, generation after generation. Constellations that ancient astronomers mapped thousands of years ago still looked almost identical to observers in the 19th century. Nothing in the sky seemed to suggest that the universe itself might be changing on the larger scales. This impression of stability shaped the way scientists imagined the cosmos. A universe that had always existed and would always exist felt like the simplest explanation. Matter filled space, stars burned steadily, and the grand structure of the cosmos remained largely the same over unimaginably long stretches of time. Even when physics advanced dramatically during the 17th and 18th centuries, this assumption remained intact. Isaac Newton's laws of motion and gravity allowed scientists to describe the movements of planets and moons with astonishing accuracy. His theory of universal gravitation explained that every object with mass attracts every other object with mass. In words that can be spoken clearly, the relationship between gravitational force, mass, and distance can be summarized as force equals the gravitational constant multiplied by the mass of the first object multiplied by the mass of the second object divided by the square of the distance between them. This equation worked beautifully for many problems. It described the motion of planets around the Sun and predicted the return of comets with remarkable precision. But when scientists tried to apply Newton's laws to the universe as a whole, a deeper question emerged. If gravity always attracts matter, then over long periods of time the universe should slowly collapse inward. Every star should pull on every other star. Eventually the entire cosmos should draw together under its own gravity. Yet the universe clearly had not collapsed. To resolve this tension, many physicists imagined that the universe must be infinitely large and evenly filled with stars. In such a perfectly balanced arrangement, gravitational forces from all directions might cancel out on average. This allowed the idea of a static universe to remain plausible. For centuries, the possibility that the universe itself might be evolving remained largely unexplored. That situation changed in the early 20th century with the arrival of a revolutionary new theory of gravity. In 1915, Albert Einstein introduced the theory of general relativity. Instead of describing gravity as an invisible force acting across space, Einstein proposed something far more subtle. According to general relativity, gravity arises from the curvature of spacetime itself. Mass and energy distort the geometry of spacetime, and objects move along paths determined by that curvature. A helpful way to imagine this idea is to picture spacetime as a flexible surface. When a massive object such as a star or planet sits on that surface, it creates a depression. Nearby objects then follow curved paths around that depression, which we perceive as gravitational attraction. In reality, the mathematics behind general relativity is far more complex than this analogy, involving curved four-dimensional spacetime described through tensor equations. But the key idea remains beautifully simple. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. When Einstein applied his equations to the universe itself, he encountered an unexpected difficulty. His mathematical description of spacetime suggested that a universe filled with matter could not remain static forever. Gravity would either cause the universe to contract inward or allow it to expand outward. A perfectly balanced, motionless cosmos appeared mathematically unstable. Einstein was uneasy about this implication. At the time, no astronomer had observed galaxies rushing away from one another, and the idea of a changing universe felt radical. To preserve the prevailing view of a stable cosmos, Einstein introduced an additional term into his equations, This term became known as the cosmological constant. The cosmological constant represented a form of energy built into spacetime itself. In Einstein's original formulation, it acted as a gentle repulsive influence that counterbalanced the attractive pull of gravity. If gravity tried to pull matter inward, the cosmological constant pushed outward, allowing the universe to remain static. In essence, Einstein adjusted his equations so the universe would behave the way scientists expected it to behave. However, other physicists soon began exploring the equations of general relativity without assuming the universe had to remain perfectly still. One of the first to do so was the Dutch astronomer Willem de Sitter. In 1917, de Sitter examined solutions to Einstein's equations that described a universe almost entirely empty of matter. To Einstein's surprise, de Sitter discovered that even in a nearly empty universe, space-time itself could expand. His model showed that expansion was not necessarily driven by matter alone. The geometry of space-time itself could evolve over time. This result hinted that the cosmos might be far more dynamic than previously imagined. A few years later, a Russian mathematician and physicist named Alexander Friedmann pushed these ideas even further. In the early 1920s, Friedmann studied Einstein's equations under the assumption that matter is distributed evenly throughout space when viewed on extremely large scales. This assumption is known as the cosmological principle, which states that the universe appears roughly uniform and isotropic when averaged over vast distances. Using this principle, Friedmann derived solutions showing that the universe could expand, contract, or even oscillate depending on its overall density and energy content. In Friedmann's mathematical description, the size of the universe changes over time, according to equations derived directly from general relativity. These equations describe how cosmic expansion depends on matter density, energy, and the curvature of spacetime. At first, Einstein believed Friedmann had made a mathematical mistake, but after reviewing the calculations, Einstein eventually acknowledged that the work was correct. Around the same period, the Belgian physicist and Catholic priest Georges Lemaitre independently reached similar conclusions. Lemaitre combined general relativity with emerging astronomical observations and proposed that the universe was expanding. He went further still, suggesting that if the universe is expanding today, then in the distant past it must have been compressed into an extremely dense state. Lemaitre famously referred to this early state as the primeval atom. These ideas began to form the mathematical backbone of modern cosmology. Over time, the combined work of Alexander Friedmann, Georges Lemaitre, Howard Robertson, and Arthur Walker produced a general description of cosmic spacetime now known as the Friedmann-Lemaitre-Robertson-Walker metric. This metric describes how distances between points in the universe change as space expands or contracts. It assumes that the universe is homogeneous and isotropic on the larger scales, meaning that it looks broadly the same in every direction and at every location when viewed across enormous cosmic distances. Within this framework, the universe is not static. Instead, it behaves like a dynamic, evolving system whose size can grow or shrink depending on its physical conditions. These mathematical insights quietly reshaped our understanding of the cosmos. Even before astronomers gathered clear observational evidence, the equations of general relativity had already begun to whisper a profound possibility. The universe might not be eternal and unchanging, it might be expanding, and if the universe is expanding today, then long ago it must have been smaller, much smaller. The stage was now set for astronomers to look outward and see whether the sky itself revealed signs of this cosmic expansion. The idea that the universe might be expanding began as a quiet suggestion hidden inside equations, but eventually astronomers turned their telescopes toward the sky to see whether reality matched the mathematics. What they found would permanently change humanity's understanding of the cosmos. In the early 20th century, astronomers were still trying to answer a fundamental question about the nature of the faint misty patches scattered across the night sky. These objects, often called spiral nebulae, had been observed for centuries through telescopes. Some scientists believed they were clouds of gas within our own Milky Way galaxy. Others suspected they might be entire galaxies far beyond our own. Resolving this debate required measuring distances on an enormous scale, and that turned out to be far from easy. Space does not come with convenient measuring sticks. Astronomers must rely on indirect methods to determine how far away distant objects truly are. One of the most important breakthroughs in this effort came from the study of a particular type of star known as a Cepheid variable. Cepheid variable stars are remarkable because their brightness changes in a regular repeating cycle. They slowly brighten and dim over time, with periods that can last several days or several weeks. At first glance, this might seem like a curious but unremarkable behaviour, but careful observation revealed something extraordinary. In 1912, the astronomer Henrietta Swan Leavitt, working at the Harvard College Observatory, discovered a precise relationship between the period of a Cepheid variable star and its true luminosity, which means its actual brightness. The longer the star takes to complete one full cycle of brightening and dimming, the brighter that star truly is. This relationship became known as the period luminosity relation. Once astronomers know how bright a star truly is, they can compare that intrinsic brightness to how bright the star appears from Earth. If the star appears faint, it must be far away. If it appears brighter, it must be closer. This method effectively turned Cepheid variables into cosmic distance markers. They became what astronomers call standard candles, objects whose true brightness is known. With this discovery, the scale of the universe suddenly became measurable in a way that had never been possible before. One astronomer who made extraordinary use of this method was Edwin Hubble. Working in the 1920s at Mount Wilson Observatory in California, Hubble had access to one of the most powerful telescopes of the time, the 100-inch Hooker telescope. Through this telescope, Hubble carefully examined several spiral nebulae that appeared faint and distant in the night sky. Inside these objects, he identified individual Cepheid variable stars. By measuring the periods of those Cepheids and applying Henrietta Leavitt's luminosity relation, Hubble was able to calculate their distances. The results were astonishing. These nebulae were far too distant to belong to the Milky Way galaxy. They were entirely separate galaxies of their own. What had once appeared as faint smudges of light were actually immense systems of billions of stars scattered across the cosmos. The universe was suddenly far larger than anyone had imagined. But Hubble's work did not stop there. Another puzzle was waiting to be understood. When astronomers examine the light from distant galaxies, they can break that light apart into a spectrum, separating it into different wavelengths. This process reveals patterns known as spectral lines, which correspond to specific chemical elements. Each element produces a unique pattern of lines, almost like a fingerprint. When scientists observed the spectra of many distant galaxies, they noticed something curious. The spectral lines appeared shifted toward the red end of the spectrum. This phenomenon is known as redshift. In physics, redshift often occurs because of the Doppler effect. When a source of waves moves away from an observer, the waves stretch out and their wavelength becomes longer. With light, longer wavelengths correspond to redder colours. Earlier in the 20th century, an astronomer named Vesto Melvin Slipher had been studying this effect carefully. Working at Lowell Observatory in Arizona, Slipher measured the spectra of numerous spiral nebulae beginning in the 1910s. His observations showed that most of these objects exhibited strong redshifts. In simple terms, their light appeared stretched toward longer wavelengths. This suggested that many of these nebulae were moving away from Earth at tremendous speeds. Some appeared to be receding at hundreds or even thousands of kilometers per second. For the early 1900s, these velocities were astonishingly large. At first, Slipher's measurements seemed puzzling. The distances to these objects were not yet known, so their motion could not be fully interpreted. But when Edwin Hubble combined his new distance measurements with Slipher's redshift data, an extraordinary pattern emerged. The farther away a galaxy appeared to be, the faster it seemed to be moving away from us. This relationship became known as Hubble's law. In simple language, Hubble's law states that the recessional velocity of a galaxy is proportional to its distance from us. Expressed in words, the relationship can be described as recessional velocity equals the Hubble constant multiplied by distance. The Hubble constant represents the rate at which the universe expands. Its exact value has been refined many times over the decades as measurements have improved. What mattered most in Hubble's original discovery was the pattern itself. Galaxies were not moving randomly, they were systematically moving away from each other. At first glance, this observation might seem to suggest that our galaxy sits at the centre of everything, with all other galaxies fleeing outward. But that interpretation quickly falls apart when we consider the larger picture. Imagine placing dots across the surface of a balloon and then slowly inflating it. As the balloon expands, every dot moves away from every other dot. No single point sits at the center of the expansion on the surface itself. The same idea applies to the universe. Space itself is stretching. As space-time expands, the distances between galaxies increase. Each galaxy observes other galaxies moving away, not because they are racing through space like rockets, but because the space between them is gradually growing. This distinction is crucial. The expansion of the universe does not describe an explosion that happened at a single point in space. Instead, the expansion happens everywhere at once. Every region of space participates in the process. When astronomers realized this, the implications were profound. If galaxies are moving apart today, then in the distant past they must have been closer together. The universe must once have been smaller, much smaller. Following this reasoning backward leads to a striking conclusion. If the expansion continues to be traced into the past, the density and temperature of the universe would increase dramatically. Eventually, everything would converge toward an extremely hot, dense state. In other words, the universe appears to have evolved from a much more compact beginning. This realization marked one of the most important turning points in the history of science. Observations of distant galaxies had revealed that the universe is not static after all. It is dynamic, it is changing, and it has been expanding for billions of years. The sky itself had confirmed what the equations of general relativity had quietly suggested. The universe is not standing still, it is growing. When astronomers say that distant galaxies are moving away from us, they are not watching galaxies glide across the sky like drifting ships. The evidence for this motion comes from something far subtler, hidden inside the light that reaches our telescopes. Light carries information. Every beam of starlight that arrives at Earth contains clues about the object that produced it. Within that light are patterns called spectral lines, which appear when atoms absorb or emit very specific wavelengths. Each chemical element leaves behind its own distinctive pattern of lines. Hydrogen produces one set of lines, helium produces another. Oxygen and carbon create their own recognizable fingerprints as well. When astronomers examine the spectrum of a star or galaxy, they can identify these patterns and determine what elements are present. But something interesting happens when the object producing the light is moving. If a source of light moves away from an observer, the wavelengths of that light become stretched. The crests of the waves spread farther apart, shifting the light toward the red end of the spectrum where wavelengths are longer. This shift toward longer wavelengths is known as redshift. If the object moves toward the observer instead, the opposite occurs. The wavelengths become compressed, shifting the light toward the blue end of the spectrum. That effect is known as blue shift. This behavior arises from a physical phenomenon called the Doppler effect. The Doppler effect appears in everyday life whenever waves are involved. A familiar example occurs when an ambulance drives past with its siren sounding. As the ambulance approaches, the sound waves are compressed and the pitch sounds higher. As it moves away, the waves stretch out and the pitch becomes lower. Light behaves in a similar way when objects move through space. For many astronomical objects, the Doppler effect does indeed explain the shifting of spectral lines. Stars orbiting within galaxies, for example, move through space relative to one another, producing small redshifts or blue shifts depending on their motion. However, when astronomers began studying distant galaxies, they discovered that something slightly different was happening. The redshift of distant galaxies was far larger than expected, and it increased systematically with distance. Galaxies billions of light-years away showed enormous shifts toward longer wavelengths. At first glance, it might seem that these galaxies are simply racing away through space at tremendous speeds. But the deeper explanation lies in the behavior of space itself. According to modern cosmology, the universe is expanding. Space is not static. Instead, the distances between galaxies increase as space-time stretches over time. When light travels across this expanding universe, the space through which the light moves gradually stretches. As space stretches, the wavelength of the light stretches with it. This process produces what astronomers call cosmological redshift. Unlike the Doppler effect, which results from motion through space, cosmological redshift occurs because the space between objects grows larger while the light is in transit. A helpful way to picture this idea is to imagine drawing a series of evenly spaced marks along a rubber band. If you stretch the rubber band, the distance between the marks increases. In a similar way, as space expands, the wavelengths of light traveling through that space become longer. The longer the light travels through expanding space, the more its wavelength stretches. This means that light arriving from extremely distant galaxies carries a record of how much the universe has expanded during its journey. In many cases, that journey lasts billions of years. Astronomers can measure this stretching with remarkable precision. By comparing the positions of known spectral lines to their expected wavelengths, scientists determine how much those lines have shifted. The amount of redshift is often described using a quantity called redshift magnitude, which indicates how much the wavelength of the light has been stretched relative to its original value. For nearby galaxies, the shift is relatively small. For galaxies extremely far away, the shift becomes dramatic. Some of the most distant galaxies ever observed show light that has been stretched several times beyond its original wavelength. Gathering these measurements requires vast observational efforts involving some of the most powerful telescopes ever constructed. One major project dedicated to mapping the large-scale structure of the universe is the Sloan Digital Sky Survey. This survey began in the early 2000s and has used a specially designed telescope located at Apache Point Observatory in New Mexico. The Sloan Digital Sky Survey has measured the spectra of millions of galaxies and quasars. By analysing the redshifts of these objects, astronomers can determine how far away they are and how quickly they appear to be receding. The result is an extraordinary three-dimensional map of the universe, extending across billions of light years. Other observatories around the world and in space contribute to this effort as well. The National Aeronautics and Space Administration, widely known as NASA, operates powerful space telescopes that observe distant galaxies at many wavelengths of light. The European Space Agency conducts similar observations through missions such as the Planck satellite and the Euclid Space Telescope. Together, these instruments allow astronomers to examine enormous portions of the cosmos and measure redshifts for galaxies across vast distances. When all of these measurements are combined, the pattern first noticed in the early 20th century becomes unmistakable. Distant galaxies consistently show redshifted light, and the farther away a galaxy is, the greater the redshift tends to be. This pattern aligns precisely with the idea that the universe is expanding. If space is stretching everywhere, then light travelling through that expanding space should also stretch. The farther the light travels, the more stretching occurs. What began as a puzzling observation of shifted spectral lines has become one of the most powerful pieces of evidence in modern cosmology. The redshift of distant galaxies tells a simple but profound story. The universe is not static, it is growing, and every beam of ancient light reaching our telescopes carries a quiet record of that expansion, written across the spectrum of the cosmos itself. Once astronomers recognized that galaxies are steadily moving away from one another, a simple but powerful idea began to emerge. If the universe is expanding today, then it must have been smaller in the past. That conclusion may sound obvious when stated plainly, but its implications are enormous. It means that the universe we see now, filled with galaxies separated by vast distances, did not always look this way. Long ago, those galaxies must have been much closer together. And if we follow that reasoning further, something even more striking appears. Go far enough back in time, and the entire universe must have been compressed into a far smaller volume than it occupies today. This process of reasoning is sometimes described as rewinding the cosmic clock. Astronomers observe how galaxies move apart today, and then ask what the universe would have looked like earlier in its history. By reversing the expansion mathematically, scientists can reconstruct the conditions that must have existed billions of years ago. The underlying logic comes directly from the equations of general relativity combined with observational data. Once the expansion rate of the universe is measured, cosmologists can estimate how long the expansion has been taking place. The key quantity involved in this calculation is the Hubble constant, the number that describes how quickly galaxies recede from one another as a function of distance. In simple terms, the Hubble constant tells us how fast space itself is stretching. If galaxies 1 million light-years away are receding at a certain speed, then galaxies twice as far away tend to recede roughly twice as fast. By measuring this relationship across enormous distances, astronomers determine the expansion rate of the universe. Once the expansion rate is known, scientists can estimate how long it would take for the universe to grow from a very small size to its present scale. Imagine watching a balloon slowly inflate. If you measure how quickly the balloon is expanding at this moment, you can estimate how long it must have been inflating to reach its current size. Cosmologists apply a similar idea to the universe itself. Modern observations suggest that the universe is approximately 13.8 billion years old. This number comes from combining measurements of cosmic expansion with observations of the cosmic microwave background and the large-scale structure of the universe. Space missions such as the Wilkinson Microwave Anisotropy Probe, often called WMAP, and the Planck satellite operated by the European Space Agency have played crucial roles in refining this estimate. These missions mapped subtle temperature variations in ancient radiation that fills the universe. By analysing those patterns using the equations of cosmology, scientists determined the age of the universe with remarkable precision. 13.8 billion years is an almost unimaginably long time, yet when viewed on cosmic scales, it represents the lifetime of the observable universe as we know it. Once this timeline is established, the next step is to consider what the universe must have been like earlier in that history. As the universe expands, matter spreads out and temperatures drop. The energy density of radiation decreases as wavelengths stretch and particles move farther apart. This means that the earlier universe must have been hotter and denser than the universe we see today. If we imagine rewinding cosmic history, galaxies begin to move closer together. The vast clusters of galaxies shrink inward. Eventually, individual galaxies overlap and merge into a much denser cosmic environment. Continue rewinding further, and the stars themselves have not yet formed. The universe becomes a hot sea of gas composed primarily of hydrogen and helium. Go back even earlier, and temperatures rise dramatically. At sufficiently high temperatures, atoms cannot exist because electrons are torn away from atomic nuclei. Matter becomes an energetic plasma of charged particles interacting with intense radiation. Still earlier, the universe becomes even more extreme. Temperatures reach billions of degrees. Atomic nuclei themselves begin to break apart under the intense heat. At this stage, matter exists as a mixture of fundamental particles such as protons, neutrons, electrons, neutrinos, and photons. The further we rewind the cosmic clock, the more energetic and compressed the universe becomes. This reasoning led scientists to a remarkable conclusion. The Big Bang Theory does not describe a single explosive event in the usual sense. Instead, it describes a long thermal history in which the universe gradually cooled as it expanded. In other words, the Big Bang model is fundamentally a theory about temperature, density, and the changing physical conditions of the early universe. It describes how the cosmos evolved from an extremely hot and dense state into the cooler, structured universe we inhabit today. This concept of a thermal history was developed and refined during the middle of the 20th century by physicists studying nuclear reactions and particle interactions. Researchers such as George Gamow, Ralph Alpher, and Robert Herman explored how the early universe would behave under extreme temperatures. They calculated how nuclear reactions might occur in those conditions and how the cooling of the universe would influence the formation of matter. Their work revealed that many features of the modern universe could be explained if the cosmos began in a hot, dense state and then expanded and cooled over billions of years. The Big Bang model therefore provides a framework that links together many different observations. It explains why galaxies are moving apart. It predicts how the chemical elements formed in the early universe. It describes why faint radiation from the early cosmos still fills space today. Perhaps most importantly, it provides a way to connect the largest structures in the universe with the smallest particles studied in physics laboratories. Cosmology becomes a bridge between astronomy and particle physics, linking the behavior of galaxies to the properties of fundamental particles. As scientists continue to trace the universe backward in time, the conditions grow increasingly extreme. Temperatures rise to levels far beyond anything we can reproduce on Earth. In those earliest moments, ordinary matter behaves in unfamiliar ways, and the laws of physics themselves become subjects of intense investigation. To truly understand how the universe began its expansion, we must explore the physics that governed those earliest epochs. Because long before galaxies, long before stars, and long before atoms themselves, the universe was a very different place. When the expansion of the universe is traced backward toward its earliest moments, the cosmos becomes steadily hotter and denser. Galaxies merge into clouds of gas, atoms break apart, and familiar structures disappear into an environment so energetic that everyday matter could not exist in its usual form. The early universe was not filled with stars or planets. It was a seething, luminous ocean of energy. To picture this environment, it helps to remember that temperature is really a measure of motion. The hotter something becomes, the faster its particles move and collide. In the early universe, those motions were extreme. Temperatures reached billions of degrees, far hotter than the core of any star that exists today. At such enormous temperatures, atoms cannot remain intact. The electrons that normally orbit atomic nuclei are stripped away by intense radiation. Instead of neutral atoms, the universe contained a plasma. A plasma is a state of matter composed of charged particles moving freely through space. Electrons, protons, and other particles move independently rather than remaining bound together. Because these particles carry electric charge, they interact strongly with radiation and magnetic fields. The early universe therefore behaved like a dense glowing plasma, in which matter and radiation were tightly coupled. Photons, which are particles of light, constantly collided with charged particles. Electrons scattered photons in every direction, preventing light from travelling very far without interacting with matter. The universe at that time was opaque, meaning that light could not move freely across large distances. This cosmic plasma was incredibly energetic. Collisions between particles occurred constantly, and the average energy of those particles was far higher than anything normally encountered in laboratories on Earth. To describe such an environment accurately, physicists must use a framework known as relativistic thermodynamics. This field combines the principles of thermodynamics, which describe heat and energy, with the equations of Einstein's theory of relativity. One of the scientists who contributed significantly to this area was Richard Chase Tolman. During the 1930s, Tolman studied how temperature, energy density, and entropy behave in systems influenced by gravity and relativity. His work helped clarify how thermal processes operate in an expanding universe. In ordinary thermodynamics, temperature and pressure influence how gases behave inside containers. In cosmology, however, the container itself is expanding. Space grows larger over time, and the energy density of matter and radiation changes as the universe evolves. Relativistic thermodynamics allows scientists to track how energy spreads out as the cosmos expands and cools. These calculations reveal that the early universe was dominated by radiation rather than matter. Photons carried a large fraction of the total energy, and their interactions with particles played a central role in shaping the evolution of the cosmos. As the universe expanded, the wavelengths of these photons gradually stretched, reducing their energy. This process caused the temperature of the universe to drop over time, but in the earlier stages, temperatures were extraordinarily high. At temperatures exceeding billions of degrees, even atomic nuclei struggle to remain stable. Nuclear reactions occur rapidly as particles collide with enormous energy. Understanding these processes became a major focus of mid-20th century physics. One of the most influential figures in this effort was the Russian-American physicist George Gamow. Gamow was known for his playful personality and creative thinking, but his scientific contributions were deeply serious. Gamow became fascinated with the idea that the early universe might have been hot enough for nuclear reactions to occur on a cosmic scale. Working with collaborators Ralph Alpher and Robert Herman in the 1940s, Gamow explored how atomic nuclei might form in the intense conditions of the early universe. Their calculations suggested that the first few minutes after cosmic expansion began would have been a critical period. During that time, protons and neutrons could collide and combine to form simple atomic nuclei. These reactions would produce hydrogen, helium, and small amounts of other light elements. The idea that the early universe functioned as a giant nuclear reactor was revolutionary. It suggested that the chemical composition of the universe could be traced back to specific physical processes occurring shortly after the beginning of cosmic expansion. Gamow and his colleagues also predicted that if the early universe had been extremely hot, remnants of that heat might still exist today in the form of faint radiation filling space. This prediction would later become one of the most important confirmations of the Big Bang model. But before reaching that point, physicists had to understand the behavior of particles and forces during the earliest cosmic eras. In modern physics, 4 fundamental forces govern the interactions of matter. These are gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Each of these forces plays a different role in the structure of the universe. Gravity controls the motion of planets, stars, and galaxies by pulling massive objects toward one another. Electromagnetism governs interactions between charged particles and produces light, electricity, and magnetism. The strong nuclear force binds protons and neutrons together inside atomic nuclei. Without it, the positively charged protons inside nuclei would repel one another and atoms could not exist. The weak nuclear force, meanwhile, is responsible for certain forms of radioactive decay and plays an important role in nuclear reactions. In the extremely hot conditions of the early universe, these forces interacted in ways that differ from what we observe today. At sufficiently high energies, some theories suggest that certain forces may merge into unified forms. Physicists studying grand unified theories investigate whether the strong nuclear force and the electro-weak force could have behaved as a single combined interaction in the earliest moments of cosmic history. Although these ideas remain areas of active research, they highlight how the early universe provides a natural laboratory for testing the deepest principles of physics. Particle interactions during this era were dominated by high-energy collisions. Protons and neutrons constantly formed and broke apart. Electrons and positrons appeared and vanished through processes of particle creation and annihilation. The entire universe behaved like an enormous particle accelerator, operating at energies far beyond those produced by machines such as the Large Hadron Collider, operated by the European Organization for Nuclear Research, often known as CERN. As the universe expanded and cooled, these intense interactions gradually slowed. Particles that once collided frequently began to separate as space stretched between them. Certain reactions stopped occurring once temperatures dropped below critical thresholds. This gradual cooling set the stage for the next major chapter in cosmic history. The early universe began as an intensely hot plasma filled with fundamental particles and radiation. But as expansion continued, temperatures fell enough to allow new structures to emerge. The first stable atomic nuclei would soon form, and those nuclei would become the building blocks for all the matter we see today. As the universe continued to expand and cool, the violent chaos of its earliest moments gradually began to settle into something slightly more organized. Temperatures that had once been unimaginably high slowly declined as space itself stretched outward. Even though the universe was still extraordinarily hot by everyday standards, conditions were changing in ways that allowed new forms of matter to emerge. One of the most important milestones in this early history occurred during a brief window of cosmic time often called Big Bang nucleosynthesis. The word nucleosynthesis simply means the creation of atomic nuclei. In this context, it refers to the formation of the first stable combinations of protons and neutrons. These combinations would become the earliest atomic nuclei in the universe. This process began only a few minutes after cosmic expansion had started. To understand why this happened at that particular time, it helps to remember the extreme environment of the early universe. At very high temperatures, particles move with enormous energy. Collisions between particles occur constantly, and many of those collisions are energetic enough to break apart atomic nuclei. Imagine trying to assemble a delicate structure while powerful explosions are going off all around you. Every time you manage to connect two pieces together, another blast immediately knocks them apart again. In the earliest moments of the universe, temperatures were so high that any attempt to form stable nuclei was quickly undone by energetic radiation. But as the universe expanded, the temperature gradually dropped. When the cosmic temperature fell to roughly 1 billion degrees, conditions finally became calm enough for certain nuclear reactions to succeed. Protons and neutrons could begin combining without being immediately destroyed by high-energy photons. This marked the beginning of Big Bang nucleosynthesis. Protons, which are the positively charged particles inside atomic nuclei, were already abundant. Neutrons, which carry no electric charge, were also present but slightly less common because some of them had already begun decaying through a process known as beta decay. When protons and neutrons collided under the right conditions, they could form a simple nucleus called deuterium. Deuterium is sometimes called heavy hydrogen because its nucleus contains one proton and one neutron. Once deuterium nuclei formed, they could collide with additional protons and neutrons to produce helium. Helium nuclei contain 2 protons and 2 neutrons bound together by the strong nuclear force. This configuration is extremely stable, making helium one of the most common products of early nuclear reactions. In addition to hydrogen and helium, a small amount of lithium also formed through a series of more complex reactions involving helium nuclei. The calculations describing these processes were carried out in detail during the 1940s by George Gamow and his collaborators Ralph Alpher and Robert Herman. Their work combined nuclear physics with cosmology to estimate how much of each element should have formed during the early universe. Gamow and his colleagues predicted that the universe should contain roughly 3/4 hydrogen and about 1/4 helium by mass, with only tiny amounts of lithium and a few other light elements. This prediction was remarkable because it could be tested through astronomical observation. If the Big Bang model was correct, then the earliest matter in the universe should still show this chemical signature. Even billions of years later, regions of space that had not been heavily altered by stars should retain these primordial proportions. Astronomers therefore began searching for environments where the original chemical composition of the universe might still be preserved. One of the most valuable places to study primordial element abundances is in extremely old stars. Some stars formed very early in cosmic history from gas clouds that had not yet been enriched by heavy elements produced in later generations of stars. These ancient stars act as time capsules, preserving clues about the chemical makeup of the early universe. Astronomers analyzed the light from these stars using spectroscopy. By spreading starlight into its component wavelengths, scientists can measure the absorption lines produced by hydrogen, helium, and other elements. The strengths of these lines reveal how much of each element is present. Another important source of information comes from intergalactic gas clouds that lie between distant galaxies. When light from a distant quasar passes through these clouds, certain wavelengths are absorbed by the atoms within them. These absorption patterns provide another way to measure the abundance of light elements in regions that have remained relatively untouched by stellar processes. Over many decades of observation, astronomers have gathered extensive data from telescopes around the world, including major facilities such as the Keck Observatory in Hawaii and the Very Large Telescope operated by the European Southern Observatory in Chile. The results have been strikingly consistent. Measurements of hydrogen, helium, and lithium abundances closely match the predictions made by Big Bang nucleosynthesis calculations. Hydrogen remains by far the most abundant element in the universe, accounting for roughly 75% of ordinary matter by mass. Helium makes up about 25%, with only trace amounts of lithium. This remarkable agreement between theory and observation provides one of the strongest pieces of evidence supporting the Big Bang model. It demonstrates that the early universe passed through a hot, dense phase in which nuclear reactions occurred on a cosmic scale. Stars also produce helium and heavier elements through nuclear fusion in their cores. However, stellar processes alone cannot explain the widespread abundance of helium observed throughout the universe. The amount of helium present is simply too large. Big Bang nucleosynthesis provides a natural explanation for this observation. It shows that helium was already present in significant quantities long before the first stars formed. This insight reveals something profound about the universe. The matter around us today carries a chemical memory of conditions that existed billions of years ago. Every hydrogen atom in your body was forged in the earliest moments of cosmic history. Many of the helium atoms drifting through space today were created within the first few minutes after the universe began expanding. These elements are ancient survivors from a time when the universe itself functioned as an immense nuclear reactor. The success of Big Bang nucleosynthesis therefore strengthens the overall cosmological picture. It links nuclear physics with astronomical observation in a way that allows scientists to test ideas about the earliest stages of cosmic evolution. And yet the story of the early universe does not end with the formation of the first nuclei. Another remarkable relic from that ancient era still fills the cosmos today. It is not made of matter, it is made of light. For the first few 100,000 years of cosmic history, the universe remained filled with a glowing plasma of charged particles and radiation. Electrons moved freely through space, atomic nuclei drifted among them, and photons constantly scattered off these charged particles in every direction. Light could not travel far without encountering another particle. The early universe was therefore opaque, much like a dense fog through which light struggles to pass. Even though the cosmos was filled with radiation, that radiation could not move freely across great distances. But as the universe continued expanding, temperatures slowly fell. Eventually the temperature dropped to roughly 3,000 degrees above absolute zero. Compared with the billions of degrees present during the earliest moments, this was a dramatic cooling. At this point, a major transformation occurred. Electrons began attaching themselves to atomic nuclei, forming stable neutral atoms for the first time. Hydrogen atoms formed when a single electron joined with a proton. Helium atoms formed when electrons bound to helium nuclei containing 2 protons and 2 neutrons. This process is called recombination, although the name is slightly misleading. It suggests something is happening again, but in reality this was the first time stable atoms could exist in the expanding universe. Once atoms formed, something remarkable happened to the light filling the cosmos. Neutral atoms do not scatter photons nearly as effectively as free electrons do. As a result, radiation that had previously been trapped within the dense plasma could suddenly travel freely. The fog lifted. Light began moving across space largely unhindered. The radiation released during this moment spread outward in every direction, filling the universe with a glow that carried information about the conditions at that time. That ancient light still exists today. It has been travelling across the cosmos for nearly the entire history of the universe. But because the universe has continued expanding, the wavelengths of that light have stretched enormously. Radiation that once had the energy of visible or infrared light has gradually been stretched into much longer wavelengths. Today, it appears in the microwave portion of the electromagnetic spectrum. This ancient radiation is known as the cosmic microwave background, often abbreviated as the CMB. For decades after the Big Bang model was first proposed, the existence of this radiation remained only a prediction. Physicists such as George Gamow, Ralph Alpher, and Robert Herman had calculated that if the early universe was once extremely hot, then some of that heat should still remain in the form of faint background radiation. Their calculations suggested that the temperature of this radiation would be only a few degrees above absolute zero. At the time, however, technology was not advanced enough to detect such faint signals. The discovery finally arrived in the mid-1960s in a rather unexpected way. 2 radio astronomers named Arno Penzias and Robert Wilson were working at Bell Telephone Laboratories in New Jersey. Their research involved a large horn-shaped radio antenna originally designed for satellite communication experiments. The antenna was extremely sensitive and capable of detecting very weak radio signals from space. While using the instrument, Penzias and Wilson noticed a persistent source of background noise. The signal appeared uniform and came from every direction in the sky. At first they suspected that something was wrong with their equipment. They carefully checked the electronics, recalibrated the antenna, and attempted to identify possible sources of interference. They considered signals from nearby cities, emissions from the atmosphere, and even noise generated by the instrument itself. Nothing seemed to explain the mysterious signal. In a detail that has become famous in the history of science, the researchers even cleaned out a pair of pigeons that had been nesting inside the antenna structure. The pigeons had left behind a substance that Penzias politely described in scientific language as white dielectric material. Removing the birds and cleaning the antenna did not eliminate the noise. The signal remained. Eventually, Penzias and Wilson learned that a group of physicists at Princeton University, led by Robert Dicke, was searching for exactly this type of radiation. Dicke and his colleagues were attempting to detect the faint thermal glow predicted by the Big Bang model. When the 2 groups compared notes, it became clear that Penzias and Wilson had accidentally discovered the long-predicted cosmic microwave background. The radiation had a temperature of about 3 degrees above absolute zero and appeared nearly identical in every direction. This discovery was extraordinary. The cosmic microwave background represents the oldest light we can observe in the universe. It originated roughly 380,000 years after cosmic expansion began, when the universe cooled enough for atoms to form and radiation was finally able to travel freely. Before that moment, light could not move unimpeded through the dense plasma of charged particles. Because of this, the cosmic microwave background acts like a photograph of the universe at that early time. It preserves a snapshot of the cosmos when it was still very young. In 1978, Arno Penzias and Robert Wilson were awarded the Nobel Prize in Physics for their discovery of this radiation. Their work provided one of the most important confirmations of the Big Bang model. The cosmic microwave background fills all of space and arrives at Earth from every direction in the sky. This uniformity reflects the fact that the early universe was remarkably smooth on large scales. The temperature of the cosmic microwave background today is about 2.7 degrees above absolute zero. Although that temperature is extremely cold by everyday standards, it represents the cooled remnant of a universe that was once intensely hot. Every second, countless photons from this ancient radiation pass silently through our planet. They pass through walls, through the atmosphere, and even through our bodies without us noticing. These photons have been travelling across space for nearly 14 billion years. Their journey began when the universe was only a tiny fraction of its current age. The existence of the cosmic microwave background tells us something profound about cosmic history. It confirms that the universe once passed through a dense hot phase in which matter and radiation were tightly coupled. It also demonstrates that the universe has been expanding and cooling ever since, yet the cosmic microwave background contains even more information than its mere existence suggests. If we examine it carefully enough, we discover that the radiation is not perfectly uniform. Tiny variations in temperature appear across the sky. These variations are incredibly small, differing by only a few parts in 100,000. But those faint patterns carry the seeds of everything that would later form in the universe. They represent the earliest hints of the cosmic structures that would eventually grow into galaxies, stars, and planets. In other words, the cosmic microwave background does not merely show us the early universe, it reveals the subtle beginnings of the entire cosmic landscape that followed. When astronomers first discovered the cosmic microwave background, it appeared almost perfectly uniform across the sky. No matter which direction radio telescopes pointed, the temperature of the radiation seemed nearly identical. This remarkable uniformity confirmed an important idea in cosmology, known as the cosmological principle, which states that the universe appears broadly the same in every direction when viewed across very large distances. But as observational technology improved, scientists began to wonder whether this ancient radiation might contain extremely small variations hidden within it. If the early universe were perfectly uniform everywhere, then matter would have remained evenly spread out as the cosmos expanded. In such a universe, galaxies, stars, and planets might never have formed, because gravity would have had no regions of slightly greater density to pull matter together. For structures to emerge, the early universe needed tiny irregularities, small pockets where matter was just slightly denser than average. These subtle differences would allow gravity to begin gathering material together over billions of years, eventually forming the cosmic structures we observe today. Detecting those variations required instruments far more sensitive than anything previously available. By the late 20th century, advances in detector technology and satellite engineering made such measurements possible. One of the first major efforts to map these ancient patterns was the Cosmic Background Explorer satellite, commonly known as COBE. The Cosmic Background Explorer was launched by the National Aeronautics and Space Administration in the late 1980s. Its goal was to measure the cosmic microwave background with unprecedented precision. COBE carried instruments designed to detect extremely faint temperature differences in the background radiation. These differences were expected to be incredibly small, perhaps only a few millionths of a degree. For several years, the satellite scanned the sky carefully, collecting data from every direction. In the early 1990s, the results were announced. COBE had detected tiny variations in the temperature of the cosmic microwave background. These variations were incredibly subtle. The temperature differences were only about 1 part in 100,000. In practical terms, this means that if the average temperature of the cosmic microwave background is roughly 2.7 degrees above absolute zero, then the variations across the sky differ by only a few 10,000ths of a degree. Despite their small size, these variations were enormously important. They represented the earliest observable traces of structure in the universe. George Smoot and John Mather, two leading scientists involved in the COBE mission, played key roles in analysing these measurements. Their work helped confirm that the faint patterns detected by the satellite matched the predictions of modern cosmology. For this achievement, Smoot and Mather were later awarded the Nobel Prize in Physics. The patterns discovered by COBE showed that the early universe contained slight density variations. Some regions were marginally denser than average, while others were slightly less dense. These density differences influenced how matter moved under the force of gravity. Where matter was a bit more concentrated, gravity pulled surrounding material inward. Over immense periods of time, these regions grew increasingly dense as more matter accumulated. Meanwhile, regions with slightly lower density gradually lost material to their surroundings. This slow amplification of tiny fluctuations eventually produced the vast cosmic structures that fill the universe today. Galaxies, clusters of galaxies, and enormous filaments of matter stretching across hundreds of millions of light-years all grew from these early irregularities. After the success of the Cosmic Background Explorer, scientists launched new missions designed to measure the cosmic microwave background with even greater accuracy. One of these missions was the Wilkinson Microwave Anisotropy Probe, often abbreviated as WMAP. The term anisotropy refers to variations that differ depending on direction. WMAP was launched by the National Aeronautics and Space Administration in the early 2000s and operated for nearly a decade. The spacecraft measured temperature variations in the cosmic microwave background with far higher resolution than COBE. Instead of detecting only the largest patterns across the sky, WMAP mapped finer structures in the radiation field. These observations revealed intricate patterns of hot and cold spots across the sky. Each spot represented a region in the early universe that was slightly denser or slightly less dense than average. The data allowed cosmologists to calculate many fundamental properties of the universe. By analyzing the distribution of temperature fluctuations, scientists determined the age of the universe with high precision. The results indicated that cosmic expansion began approximately 13.8 billion years ago. The measurements also revealed the overall composition of the universe. They showed that ordinary matter, the kind that forms stars, planets, and living beings, accounts for only a small fraction of the cosmos. A much larger portion consists of dark matter and dark energy, two mysterious components that influence cosmic structure and expansion. Another major step forward came with the Planck Space Observatory, launched by the European Space Agency in the early 2010s. The Planck satellite carried instruments capable of measuring the cosmic microwave background with even greater sensitivity than previous missions. Its detectors could identify temperature variations at extremely fine scales across the sky. The maps produced by Planck are among the most detailed images of the early universe ever created. These maps display a delicate pattern of fluctuations across the entire sky. Each tiny variation reflects a region where the density of matter differed slightly from its surroundings when the universe was still very young. Although these differences were minuscule, they provided the seeds from which all cosmic structure grew. Computer simulations performed by research groups around the world show how these initial density variations evolve over billions of years. Under the influence of gravity, slightly denser regions attract more matter, becoming the cause of future galaxies and galaxy clusters. Surrounding matter flows along vast filaments of dark matter, forming a structure sometimes called the cosmic web. Observations from large telescopes, including those operated by the European Southern Observatory and major observatories in North America and Asia, reveal galaxy distributions that closely resemble these simulated structures. The alignment between theory, simulation, and observation is one of the great successes of modern cosmology. The temperature fluctuations in the cosmic microwave background therefore represent far more than random noise. They provide a detailed record of the early universe and contain the information needed to determine many of its fundamental characteristics. From these patterns, scientists can estimate the geometry of space-time, measure the density of matter and radiation, and test predictions of theories such as cosmic inflation. All of this information is encoded within faint variations in radiation that began its journey across the cosmos nearly 14 billion years ago. What once appeared to be a perfectly uniform glow now reveals a rich tapestry of information about the earlier stages of cosmic history. And within those tiny variations lies the blueprint for the entire universe that followed. When the universe was very young, the tiny fluctuations preserved in the cosmic microwave background represented only the faintest hints of structure. Some regions contained slightly more matter than average, while others contained slightly less. The differences were incredibly small, only a few parts in 100,000. Yet those tiny irregularities would eventually grow into everything we see in the universe today. The mechanism responsible for this transformation is gravity. Gravity is the force that attracts objects with mass toward one another. Even a very small excess of matter in one region of space creates a slightly stronger gravitational pull than its surroundings. Over time, that extra pull begins to draw additional material inward. Imagine placing a small pebble in a shallow pool of water and then allowing tiny droplets to fall around it. If one droplet lands slightly closer to the pebble than the others, gravity will pull it inward more strongly, causing additional droplets to follow. Gradually, the small concentration grows larger. In the universe, this process unfolded across enormous scales and over vast stretches of time. Regions that were slightly denser than average began pulling matter inward through gravitational attraction. As matter accumulated, the gravitational pull became stronger, attracting even more material. This feedback process is sometimes described as gravitational instability. Small differences in density gradually grow larger as gravity amplifies them. Over millions and then billions of years, these growing concentrations of matter formed the first large cosmic structures. But gravity acting on ordinary matter alone would not have been sufficient to produce the galaxies we see today within the available time. Cosmologists realized that another ingredient must be involved. This ingredient is known as dark matter. Dark matter is a form of matter that does not emit light, reflect light, or interact with electromagnetic radiation in any obvious way. It cannot be seen directly with telescopes, yet its gravitational influence appears throughout the universe. The concept of dark matter emerged from several independent lines of evidence during the 20th century. One of the most influential discoveries came from the work of the American astronomer Vera Rubin. During the 1970s, Rubin studied how stars move within spiral galaxies. Using spectroscopic observations, she measured the rotational speeds of stars at different distances from the centers of galaxies. According to the laws of gravity, stars farther from the center of a galaxy should orbit more slowly, much like the outer planets of our solar system move more slowly than the inner planets. In simple terms, the expected relationship can be described as orbital velocity equals the square root of the gravitational constant multiplied by the mass enclosed within the orbit, divided by the distance from the center. If most of a galaxy's mass were concentrated near its center, stars at larger distances should move more slowly as the gravitational influence weakens. But Rubin's observations revealed something surprising. Stars in the outer regions of spiral galaxies were orbiting at nearly the same speed as stars closer to the center. Their rotational velocities remained roughly constant even at very large distances. These measurements produced what astronomers call flat rotation curves. The implication was clear. The visible matter in galaxies did not account for enough mass to produce the observed gravitational pull. Something invisible was providing additional gravity. This unseen component became known as dark matter. Further observations supported this conclusion. Galaxy clusters showed gravitational effects that could not be explained by visible matter alone. Light from distant galaxies was sometimes bent by gravitational lensing, revealing the presence of large amounts of hidden mass along the line of sight. Today, most cosmologists believe that dark matter makes up roughly 5 times as much mass as ordinary matter in the universe. Although its exact nature remains unknown, dark matter plays a crucial role in the formation of cosmic structure. Unlike ordinary matter, dark matter does not interact strongly with radiation. During the early stages of the universe, while normal matter was tightly coupled to photons in the hot plasma, dark matter could begin clumping together under gravity. These early clumps formed gravitational scaffolding that helped guide the later formation of galaxies. As the universe cooled and ordinary matter became free to move independently of radiation, it began falling into the gravitational wells created by dark matter concentrations. Over time, enormous halos of dark matter formed around growing galaxies. Within these halos, gas clouds collapsed and cooled, eventually forming the first stars. Understanding these processes requires more than simple equations. The interactions between gravity, dark matter, gas dynamics, and cosmic expansion are extremely complex. To study them in detail, cosmologists rely on large computer simulations. Research groups at institutions such as the Kavli Institute for Cosmological Physics at the University of Chicago, the Max Planck Institute for Astrophysics in Germany, and other leading centers run simulations that model the evolution of the universe over billions of years. These simulations begin with the tiny density fluctuations observed in the cosmic microwave background. Using the equations of gravity and fluid dynamics, they calculate how matter evolves as the universe expands. The results reveal an extraordinary pattern. Instead of forming a random scattering of galaxies, matter organizes itself into an enormous interconnected network known as the cosmic web. In this structure, galaxies and galaxy clusters lie along vast filaments of matter that stretch across hundreds of millions of light years. Between these filaments lie enormous voids, regions where relatively little matter exists. Galaxy clusters form at the intersections of these filaments, where gravitational attraction pulls matter together from multiple directions. Some clusters contain thousands of galaxies bound together by gravity. The largest clusters span several million light years and contain vast reservoirs of hot gas, emitting powerful X-ray radiation. Observations from major astronomical surveys, including the Sloan Digital Sky Survey and the Dark Energy Survey, reveal galaxy distributions that closely resemble the patterns predicted by these simulations. The agreement between observation and simulation provides strong evidence that the basic picture of structure formation is correct. From the faintest fluctuations in the early universe, gravity gradually sculpted the complex cosmic landscape we see today. Galaxies formed, clusters assembled, filaments stretched across the cosmos like enormous threads connecting distant regions of space. The universe that began as a nearly uniform plasma slowly evolved into a richly structured system filled with galaxies, stars, and planets. And underlying much of this cosmic architecture lies the quiet, gravitational influence of dark matter, shaping the universe in ways we are only beginning to understand. As astronomers studied the growth of galaxies and clusters across the universe, a strange realization slowly became impossible to ignore. Most of the matter-shaping cosmic structure appears to be invisible. Telescopes reveal billions of stars glowing across the night sky. Galaxies shine with enormous brilliance. Clouds of gas radiate energy at many wavelengths. Yet when scientists carefully calculate the gravitational forces holding these systems together, the visible matter simply does not add up. Something else must be there. Something that cannot be seen directly. The first strong clues appeared during the early part of the 20th century in the work of a Swiss astronomer named Fritz Zwicky. In the 1930s, Zwicky was studying a large collection of galaxies known as the Coma Cluster. This cluster lies roughly 300 million light-years away from Earth and contains thousands of individual galaxies bound together by gravity. Zwicky measured how fast the galaxies in the cluster were moving relative to one another. These motions can be determined by observing shifts in the spectral lines of each galaxy's light, allowing astronomers to calculate their velocities. Once those velocities are known, the laws of gravity can be used to estimate how much mass is required to keep the cluster gravitationally bound. The principle is straightforward. If galaxies in a cluster are moving very quickly, then a large amount of mass must be present to prevent them from escaping the cluster entirely. The relationship can be described in simple terms as the total gravitational binding mass equals a quantity proportional to the average squared velocity of galaxies multiplied by the size of the cluster and divided by the gravitational constant. When Zwicky performed this calculation, he found something startling. The galaxies in the Coma Cluster were moving far too quickly to be held together by the visible matter alone. In order for the cluster to remain stable, it would need several times more mass than astronomers could observe through telescopes. Zwicky concluded that the cluster must contain a large amount of unseen matter. He referred to this mysterious component as Dunkle Materie, the German phrase for dark matter. At the time, many scientists regarded this idea with skepticism. Observational astronomy was still developing rapidly, and the possibility remained that measurements might be incomplete or misunderstood. But over the following decades, additional evidence steadily accumulated. One of the most compelling pieces of evidence came from observations of spiral galaxies. As discussed earlier, Vera Rubin and her collaborator Kent Ford studied the rotation curves of galaxies during the 1970s. They discovered that stars in the outer regions of spiral galaxies orbit their galactic centers much faster than expected based solely on the visible mass. If only the stars and gas that telescopes can see were responsible for gravity, then the outer stars should move more slowly as their distance from the galactic center increases. Instead, Rubin observed that the rotational speed remained nearly constant even far from the center of the galaxy. These flat rotation curves indicate that galaxies are surrounded by vast halos of unseen matter, extending far beyond their visible disks. In other words, most of the gravitational mass of a galaxy is not located in its stars. It lies in an invisible halo surrounding the galaxy. Further evidence comes from a phenomenon known as gravitational lensing. According to Einstein's theory of general relativity, massive objects bend the path of light traveling near them. This effect can cause distant galaxies to appear distorted or magnified when their light passes near a massive foreground object. By studying these distortions, astronomers can measure the total mass of the intervening object, even if that mass is invisible. Observations of galaxy clusters using gravitational lensing repeatedly reveal far more mass than can be accounted for by stars and gas alone. One famous example involves the Bullet Cluster, a system where two galaxy clusters have collided. Observations from the Chandra X-ray Observatory operated by the National Aeronautics and Space Administration, combined with gravitational lensing measurements from the Hubble Space Telescope, show that most of the cluster's mass lies in regions where little visible matter is present. These results strongly support the idea that dark matter behaves differently from ordinary matter. While normal gas clouds collide and slow down during a cluster collision, dark matter appears to pass through largely unaffected, interacting primarily through gravity. Today, the leading cosmological model suggests that dark matter makes up about 27% of the total energy content of the universe. By comparison, ordinary matter, the atoms that form stars, planets, and living organisms, accounts for only about 5%. The remaining majority of the universe consists of an even more mysterious component known as dark energy. Despite the overwhelming evidence for dark matter's gravitational effects, its true nature remains unknown. Scientists have proposed many possible candidates. One class of hypothetical particles is known as weakly interacting massive particles, often abbreviated as WIMPs. These particles would possess mass but interact extremely weakly with ordinary matter, making them very difficult to detect. Another candidate is the axion, a lightweight particle originally proposed to solve certain problems in particle physics. Physicists around the world have built experiments designed to detect these particles directly. Some experiments are located deep underground in laboratories shielded from cosmic radiation. The Large Underground Xenon experiment in South Dakota and the Xenon detector located at the Gran Sasso Laboratory in Italy are examples of such efforts. Other searches take place at particle accelerators such as the Large Hadron Collider, operated by the European Organization for Nuclear Research. Astronomers also look for indirect evidence by observing regions where dark matter might annihilate or decay, potentially producing detectable signals. So far, none of these experiments has definitively identified a dark matter particle. This ongoing mystery makes dark matter one of the most fascinating puzzles in modern physics. We know it exists because its gravitational influence shapes galaxies and clusters across the cosmos, yet we still do not know exactly what it is. Understanding dark matter is essential for explaining how the universe evolved from its nearly uniform beginnings into the richly structured cosmos we observe today. Invisible though it may be, dark matter acts as a hidden framework underlying the architecture of the universe, and until its true nature is revealed, it will remain one of the deepest unanswered questions in cosmology. By the closing years of the 20th century, astronomers believed they had a reasonably clear picture of the universe's expansion. Galaxies were moving away from one another, and the expansion rate could be measured using the Hubble constant. Gravity from all the matter in the universe should gradually slow this expansion over time. The mutual attraction between galaxies and clusters would act like a cosmic brake, gently reducing the expansion speed as billions of years passed. In this picture, the universe was expanding, but the expansion should be slowing down. That expectation seems straightforward. Gravity pulls things together. If the universe contains matter, then gravity should oppose the outward motion of expansion. For decades, cosmologists tried to measure exactly how quickly that slowing might be happening. To do this, astronomers needed reliable ways to measure extremely large cosmic distances. One of the most powerful tools for this task involves a particular type of stellar explosion known as a Type I supernova. A supernova is an explosion that occurs when a star reaches the end of its life and undergoes a catastrophic collapse or detonation. Type I. A supernovae are especially valuable because they behave in a remarkably consistent way. These explosions occur when a white dwarf star in a binary system accumulates matter from a companion star. Once the white dwarf reaches a critical mass threshold, nuclear reactions ignite suddenly, and the star detonates with extraordinary brightness. Because these explosions reach nearly the same intrinsic brightness each time they occur, astronomers can use them as what are known as standard candles. If scientists know how bright the explosion truly is, they can compare that intrinsic brightness to how bright it appears from Earth. The difference reveals how far away the explosion occurred. By observing many supernovae across vast distances, astronomers can trace how the expansion of the universe has changed over time. During the 1990s, 2 international research teams undertook ambitious projects to measure distant Type I supernovae. One group was known as the Supernova Cosmology Project, led by physicist Saul Perlmutter at the Lawrence Berkeley National Laboratory in California. The other group was called the High Z Supernova Search Team, led by astronomers Brian Schmidt and Adam Rees. Both teams searched the sky for extremely distant supernova explosions occurring in galaxies billions of light-years away. By comparing the brightness of these supernovae with their redshift, scientists could determine how the expansion of the universe behaved in the past. The results were unexpected. Instead of showing evidence that the expansion of the universe was slowing down, the observations revealed the opposite. The distant supernovae appeared slightly dimmer than expected, indicating that they were farther away than predicted by models in which expansion gradually decelerates. The simplest explanation for this result was astonishing. The expansion of the universe is not slowing down, it is speeding up. The universe is undergoing accelerated expansion. This discovery fundamentally changed modern cosmology. Instead of a universe gradually slowing under the pull of gravity, observations indicated that some unknown influence was pushing space itself to expand faster and faster over time. To explain this phenomenon, scientists introduced the concept of dark energy. Dark energy refers to a form of energy that permeates all of space and produces a repulsive gravitational effect. Unlike ordinary matter and dark matter, which tend to pull structures together through gravity, dark energy appears to drive space apart. The exact nature of dark energy remains one of the greatest mysteries in physics. What we know about it comes primarily from its large-scale effects on cosmic expansion. Measurements from supernova observations, studies of the cosmic microwave background, and surveys of galaxy distributions all suggest that dark energy dominates the present energy content of the universe. In fact, modern cosmological measurements indicate that roughly 68% of the universe consists of dark energy. Dark matter accounts for approximately 27%. Ordinary matter, including every star, planet, gas cloud, and living organism, makes up only about 5%. These proportions form the basis of what cosmologists call the lambda cold dark matter model, often abbreviated as the lambda CDM model. This model serves as the standard framework for understanding the large-scale behavior of the universe. The term lambda refers to the Greek letter traditionally used to represent the cosmological constant in Einstein's equations of general relativity. Cold dark matter describes the type of dark matter believed to exist in the universe. The word cold in this context means that the particles move relatively slowly compared with the speed of light, allowing them to clump together and form the gravitational scaffolding that shapes galaxies and clusters. Within the lambda CDM model, the expansion of the universe is influenced by three major components. Ordinary matter contributes gravitational attraction. Dark matter provides additional gravitational pull that helps form cosmic structures. Dark energy produces a repulsive effect that accelerates the expansion of space. Mathematically, the influence of the cosmological constant appears as an additional term in Einstein's gravitational equations. In simplified language, the relationship can be described as the curvature of spacetime equals the energy and momentum of matter and radiation plus an additional constant energy density associated with the cosmological constant. Einstein originally introduced this constant in an attempt to keep the universe static. Later, when evidence for expansion emerged, he reportedly referred to the cosmological constant as his greatest mistake. Yet modern cosmology has revived the concept in a new form. If dark energy behaves like a constant energy density filling space, then it may be closely related to Einstein's cosmological constant after all. In this sense, an idea once introduced to prevent cosmic expansion may now help explain why the expansion is accelerating. Even with this framework in place, many questions remain unanswered. Scientists still do not know whether dark energy truly behaves like a constant energy density, or whether it evolves over time. Some theories propose that dark energy might arise from quantum fields permeating space. Others explore the possibility that our understanding of gravity itself may require modification on extremely large scales. Astronomical surveys continue searching for clues. Projects such as the Dark Energy Survey and the Euclid Space Mission, operated by the European Space Agency, map the distribution of galaxies across vast regions of space. By studying how cosmic structures evolve, researchers hope to learn more about the nature of the force driving cosmic acceleration. The discovery of dark energy revealed that the universe is even stranger than scientists had imagined. The cosmos is not only expanding, it is expanding faster and faster with time, and the mysterious energy responsible for this acceleration now dominates the fate of the universe itself. As cosmologists continued studying the early universe, a puzzling question slowly emerged. The universe appeared remarkably uniform. When scientists measured the cosmic microwave background radiation, they found that its temperature was almost exactly the same in every direction. The variations were incredibly small, only a few parts in 100,000. At first glance, this uniformity might seem unremarkable, but when researchers examined the implications more carefully, they realized that something strange was happening. Regions of the universe separated by enormous distances seemed to share nearly identical physical properties. Yet according to ordinary cosmic expansion, many of these regions should never have been in contact with one another. Light itself travels at a finite speed, and there simply had not been enough time in the early universe for information or energy to pass between those distant regions. This puzzle became known as the horizon problem. In simple terms, the horizon problem asks why parts of the universe that are far beyond each other's observable horizons appear to have nearly identical temperatures. Another related puzzle concerned the overall geometry of the universe. Measurements of cosmic expansion and radiation suggested that the large-scale geometry of the universe is very close to what physicists call spatial flatness. In a flat universe, the geometry follows the familiar rules of Euclidean space, meaning that parallel lines remain parallel and the angles of a triangle add up to 180 degrees. However, theoretical calculations showed that maintaining this precise balance would require extremely fine-tuning in the earliest moments of cosmic history. Even a tiny deviation from flatness should have grown dramatically over time, leading either to rapid collapse or runaway expansion. Yet the universe today appears astonishingly close to perfectly balanced. This difficulty became known as the flatness problem. By the late 1970s, cosmologists were searching for explanations that could resolve both of these puzzles simultaneously. One of the most influential proposals came from a young physicist named Alan Guth. While working at the Stanford Linear Accelerator Center in the late 1970s, Guth was studying ideas related to particle physics and phase transitions in the early universe. These phase transitions occur when physical conditions change in ways that alter the behavior of fundamental fields. A familiar example of a phase transition occurs when water freezes into ice or boils into steam. In the early universe, similar transitions may have occurred within the fields governing particle interactions. Guth realized that under certain conditions, these transitions might produce a brief period of extremely rapid expansion. This expansion would occur far faster than the normal cosmic growth described by the Hubble expansion. The idea became known as cosmic inflation. According to the inflationary model, the universe experienced an incredibly brief but dramatic expansion during the earliest fraction of a second after cosmic expansion began. During this period, space itself expanded exponentially. Regions that were once extremely small were stretched to enormous sizes in a tiny fraction of a second. Although inflation lasted for only a fleeting moment, its effects would shape the entire universe. One way to imagine this process is to picture a tiny patch of space expanding like a balloon that suddenly inflates thousands of times faster than usual. Before inflation, the region might have been smaller than an atomic nucleus. After inflation, that same region could expand to astronomical scales. This dramatic stretching helps resolve the horizon problem. If the universe began as a small region in which temperature and energy were evenly distributed, then inflation could stretch that tiny uniform region into a vast cosmic expanse. Regions of the universe that appear distant today would once have been close enough to interact and equalize their temperatures. Inflation also helps explain the flatness problem. Rapid expansion would smooth out any initial curvature in spacetime, much like stretching a small curved surface makes it appear flatter when viewed over larger distances. A helpful analogy is the surface of Earth. At small scales, the ground appears flat, even though the planet itself is curved. Similarly, inflation would stretch spacetime so dramatically that the universe appears almost perfectly flat across the observable region. After Alan Guth introduced the concept of inflation in the early 1980s, other physicists developed more refined versions of the theory. One important contribution came from the Russian physicist Andrei Linde. Linde proposed a version of inflation known as chaotic inflation. In this model, inflation does not occur only once in a single location. Instead, different regions of space may undergo inflation at different times, leading to a complex and evolving cosmic landscape. Some regions stop inflating and form universes like our own, while other regions continue expanding. This idea opened the door to the possibility that our universe might be only one part of a much larger structure. Theoretical physicist Alexander Vilenkin further explored the implications of inflation for the origin of the universe itself. Vilenkin studied models in which the universe might arise through quantum processes that allow space and time to emerge from extremely small initial conditions. Another important perspective came from the collaboration between physicists James Hartley and Stephen Hawking. Their work on the so-called no-boundary proposal suggested that the earliest moments of the universe might not involve a sharp beginning in time. Instead, time itself could behave differently under extreme conditions, smoothing out the boundary between past and present. While these ideas remain deeply theoretical, they demonstrate how cosmology connects the larger structures in the universe with the smaller scales studied in quantum physics. Perhaps most importantly, inflation makes predictions that can be tested through observation. According to the theory, tiny quantum fluctuations in the earliest moments of cosmic history would have been stretched to cosmic scales during the inflationary expansion. These fluctuations would later appear as the small temperature variations observed in the cosmic microwave background. When satellites such as the Wilkinson Microwave Anisotropy Probe and the Planck Space Observatory measured the patterns in the cosmic microwave background, scientists found that the statistical properties of those fluctuations closely matched the predictions of inflationary theory. The fluctuations follow a pattern known as a nearly scale invariant spectrum, meaning that variations appear across many different sizes in a way that inflation naturally produces. This agreement does not prove that inflation occurred exactly as theorists imagine it, but it provides strong evidence that something like inflation may have shaped the earliest moments of the universe. If the theory is correct, then the cosmos we observe today was once compressed into an incredibly tiny region that expanded with extraordinary speed during its earliest instant. The vast universe filled with galaxies and clusters would therefore be the result of a brief but dramatic burst of expansion that took place long before the first atoms formed. Inflation, if it truly occurred, may represent one of the most important events in the entire history of the cosmos. For many decades, the Big Bang model has provided the dominant explanation for how the universe evolved from a hot, dense beginning into the vast cosmic landscape we observe today. Yet even within this framework, scientists have continued to explore deeper questions about what might have happened at the very beginning. When cosmologists trace the equations of general relativity backward in time, the density and temperature of the universe increase dramatically. Eventually, the mathematics leads to a point where density becomes infinite, and the known laws of physics break down. This hypothetical point is often called the Big Bang singularity. A singularity does not necessarily represent a real physical object. Instead, it marks a boundary where our current theories can no longer describe what happens. It signals that something important is missing from our understanding. Because of this limitation, many physicists have explored alternative ideas suggesting that the Big Bang might not represent the absolute beginning of everything. Instead, the universe might have emerged from earlier phases or cycles that preceded the expansion we observe today. One family of ideas proposes that the universe undergoes repeated cycles of expansion and contraction. In these cyclic models, the cosmos expands for billions of years, gradually slows, and eventually begins to contract under the pull of gravity. As the universe shrinks, densities rise again until conditions become extreme enough to trigger a new expansion phase. In this picture, the Big Bang would represent the transition between a previous contracting universe and the expanding universe we inhabit now. The concept of cyclic cosmology has appeared in different forms throughout the history of physics. Early discussions of cyclic universes were explored by scientists such as Richard Tolman in the early 20th century. Modern versions of the idea draw on developments in particle physics and higher dimensional theories. One of the most influential modern proposals is known as the ekpyrotic universe model. This idea was developed by physicists Paul Steinhardt and Neil Turok in the early 2000s. The word ekpyrotic comes from an ancient Greek philosophical term meaning conflagration, or rebirth through fire. In the ekpyrotic model, the universe exists within a higher dimensional space sometimes called the bulk. Within this larger space, our observable universe may exist as a three-dimensional surface known as a brane. According to the theory, cosmic expansion could be triggered when two such branes collide within the higher dimensional space. The collision releases enormous energy, creating conditions similar to those predicted by the Big Bang model. After the collision, the universe expands and cools, allowing galaxies and stars to form. Eventually another collision could occur, beginning the cycle again. In this scenario, the Big Bang is not the ultimate beginning, but rather a transition between cosmic cycles. Another intriguing approach arises from a branch of theoretical physics known as loop quantum gravity. Loop quantum gravity attempts to unify general relativity with the principles of quantum mechanics. One of the leading figures in this field is physicist Abhay Ashtekar. In loop quantum cosmology, the geometry of spacetime is not continuous, but instead composed of discrete quantum units. At extremely small scales, spacetime behaves more like a network of interconnected loops rather than a smooth fabric. When scientists apply these ideas to the earliest universe, they find that the equations of loop quantum gravity may prevent the formation of a true singularity. Instead of collapsing into an infinitely dense point, the universe could reach an extremely high density and then rebound outward. This event is often described as a quantum bounce. In such a model, a previous universe might have been contracting before reaching this quantum limit. When the density became sufficiently large, quantum effects would reverse the collapse and initiate a new phase of expansion. The Big Bang would therefore represent a bounce rather than a beginning. Another fascinating perspective comes from the British mathematical physicist Roger Penrose. Penrose proposed a theory called conformal cyclic cosmology. In this model, the universe evolves through an endless sequence of cosmic eras, which Penrose refers to as eons. Each aeon begins with a Big Bang-like expansion, and eventually evolves toward an extremely diffuse state dominated by radiation. As the universe expands for trillions upon trillions of years, galaxies drift apart and stars eventually burn out. Black holes slowly evaporate through a quantum process known as Hawking radiation, named after physicist Stephen Hawking. Eventually the universe becomes an almost empty sea of radiation and elementary particles. Penrose argues that under these conditions, the distinction between extremely large scales and extremely small scales begins to disappear. Through a mathematical transformation known as conformal rescaling, the remote future of one aeon could be mapped onto the beginning of the next. In other words, the end of one universe might naturally lead to the birth of another. Penrose and his collaborators have even suggested that faint patterns in the cosmic microwave background might contain traces of events that occurred in a previous eon. These claims remain controversial and are still being debated within the scientific community. Despite their differences, all of these models share a common goal. They attempt to resolve the problem of the Big Bang singularity by introducing new physics that operates under extreme conditions. General relativity works extremely well for describing gravity across large distances. But near a singularity, where densities and energies become enormous, quantum effects likely play a crucial role. Developing a complete theory that combines quantum mechanics with gravity remains one of the greatest challenges in modern physics. Until such a theory is fully understood, cosmologists will continue exploring a variety of possibilities for the origin of cosmic expansion. Some of these ideas suggest that the Big Bang truly marked the beginning of space and time. Others propose that the universe emerged from earlier cycles or quantum processes. Each possibility pushes the boundaries of our understanding and reveals how much there is still to learn about the deepest structure of the cosmos. What remains certain is that the Big Bang model describes the universe remarkably well once cosmic expansion is underway. Yet the question of what came before, or whether there was a before at all, continues to inspire some of the most imaginative ideas in modern science. The theory of cosmic inflation was originally proposed to explain several puzzling features of the early universe. Its purpose was to solve problems such as the horizon problem and the flatness problem by introducing a brief period of extremely rapid expansion during the earliest fraction of cosmic history. But as physicists explored the mathematics of inflation more deeply, they discovered that the theory might lead to something even more extraordinary. Under certain conditions, inflation may never fully end. Instead of occurring only once in a single region of space, inflation could continue indefinitely in different parts of the universe. This idea is known as eternal inflation. To understand how this might happen, it helps to imagine inflation as a process driven by a field of energy that fills space. In many models, this field behaves somewhat like a ball rolling down a hill. As the field slowly loses energy, inflation ends and ordinary cosmic expansion begins. However, quantum physics introduces an element of unpredictability. Even while the field is gradually losing energy overall, small quantum fluctuations can cause parts of space to gain energy temporarily. In some regions, inflation may continue for longer periods, while other regions stop inflating and evolve into expanding universes like our own. This process can repeat again and again. As a result, inflation may generate an enormous collection of separate expanding regions scattered throughout a much larger space-time. Each of these regions behaves like its own universe. Theoretical physicists often refer to these regions as bubble universes. The idea of bubble universes was explored extensively by scientists such as Andrei Linde and Alexander Vilenkin. Their work suggested that once inflation begins, the creation of new expanding regions may continue indefinitely. Our observable universe would therefore be only one bubble within a much larger cosmic structure. In this scenario, the total universe could be vastly larger than the region we can observe. The observable universe, defined as the portion of space from which light has had time to reach us since cosmic expansion began, extends roughly 46 billion light-years in every direction. But if eternal inflation is correct, then beyond that observable horizon there could exist countless other regions, each potentially governed by slightly different physical conditions. Some bubble universes might contain galaxies and stars much like our own. Others might expand too rapidly for structure to form. Some could have different values for fundamental physical constants. In other words, the laws of physics themselves might vary from one region to another. The possibility of multiple universes existing beyond our observable horizon led to a broader concept known as the multiverse. The term multiverse refers to the idea that our universe may be only one member of a much larger collection of universes. Physicist Max Tegmark proposed a classification system that organizes different multiverse concepts into several levels. In what Tegmark called a Level 1 multiverse, the universe simply extends far beyond our observable region. Because space may be infinite, distant regions could contain arrangements of matter similar to those in our own cosmic neighborhood. In a Level 2 multiverse, inflation creates many bubble universes with potentially different physical constants, or laws of physics. Tegmark also described more speculative possibilities, including Level 3 and Level 4 multiverses involving ideas from quantum mechanics and mathematical structures. These deeper levels explore the possibility that many versions of reality may exist simultaneously, or that all mathematically possible universes might have physical existence. While these ideas stretch far beyond everyday intuition, they arise naturally from attempts to understand the implications of modern theoretical physics. Another intriguing line of research explores the connection between cosmology and the holographic principle. The holographic principle emerged from studies of black hole physics and quantum gravity. Physicists including Gerard 't Hooft and Leonard Susskind developed the idea that the information contained within a volume of space might be fully described by information stored on its boundary. In other words, the physics of a three-dimensional region could be encoded on a two-dimensional surface. Building on these ideas, physicist Raphael Bousso has investigated how holographic principles might apply to cosmology. Bousso's work explores limits on the amount of information and entropy that can exist within regions of spacetime. These ideas may help clarify how quantum gravity operates in an expanding universe and how different regions of spacetime relate to one another. Some versions of holographic cosmology suggest that the structure of the universe may be deeply connected to information theory. Although these concepts remain highly theoretical, they demonstrate how modern cosmology often intersects with the most fundamental questions in physics. The multiverse hypothesis remains one of the most controversial ideas in contemporary science. One reason for this controversy is that many versions of the multiverse are difficult to test directly. If other universes lie beyond our observable horizon, light from those regions may never reach us. Without observational evidence, scientists must rely on indirect clues and theoretical consistency. Some researchers argue that multiverse theories risk drifting into the realm of philosophy rather than empirical science. Others believe that the mathematical frameworks supporting these ideas are too compelling to ignore. Even critics often acknowledge that the possibility of multiple universes arises naturally within certain inflationary models. For now, the multiverse remains a fascinating possibility rather than a confirmed feature of reality. Yet the concept serves an important role in cosmology. It reminds us that the observable universe may represent only a tiny portion of a much larger cosmic landscape, and it encourages scientists to explore how fundamental physical laws might operate under conditions far beyond the limits of our current observations. In this way, the idea of the multiverse pushes cosmology toward deeper questions about the nature of reality itself. It challenges us to consider whether the universe we inhabit is unique, or whether it may be one of many possible cosmic worlds scattered across an even grander expanse of space-time. One of the most profound questions in cosmology concerns the overall shape of the universe itself, not simply the distribution of galaxies or the arrangement of cosmic structures, but the deeper geometry of space on the largest possible scales. When scientists speak about the geometry of the universe, they are referring to how space behaves when measured across enormous distances. The answer to this question influences how light travels, how galaxies move, and even how the universe may evolve over billions of years. Geometry in cosmology comes directly from Einstein's theory of general relativity. In this framework, mass and energy shape the curvature of space-time. The presence of matter bends space in ways that affect the paths followed by light and matter. If enough matter is present, space may curve in on itself. If too little matter exists, space may curve outward. And under very specific conditions, space may remain almost perfectly flat. Cosmologists therefore study the universe's geometry by measuring how matter and energy influence cosmic expansion. There are three primary possibilities. In a flat universe, space follows the familiar rules of Euclidean geometry. Parallel lines remain parallel forever, and the angles of a triangle add up to exactly 180 degrees. On very large scales, the geometry behaves much like the space we experience in everyday life. In an open universe, space has negative curvature. This geometry resembles a saddle shape, where parallel lines slowly diverge from one another. In such a universe, the angles of a triangle would add up to less than 180 degrees. A closed universe has positive curvature, similar to the surface of a sphere. In that geometry, parallel lines eventually converge, and the angles of a triangle add up to more than 180 degrees. These possibilities might sound abstract, but they have measurable consequences. By studying the distribution of matter, the expansion rate of the universe, and the behavior of light traveling across cosmic distances, astronomers can estimate which geometry best describes reality. One of the most powerful tools for this investigation comes from the cosmic microwave background. The tiny fluctuations in temperature within this ancient radiation contain information about the geometry of space-time when the universe was only a few 100,000 years old. In particular, cosmologists examine the angular size of these fluctuations. If the universe is flat, the patterns in the cosmic microwave background appear at one specific scale across the sky. If space is curved positively or negatively, those patterns appear slightly larger or smaller because light travels along curved paths. Precise measurements from satellites such as the Wilkinson Microwave Anisotropy Probe and the Planck Space Observatory indicate that the observable universe is extremely close to flat. Within the limits of current observations, the geometry of space appears remarkably balanced. Yet geometry is only part of the story. Another concept known as topology explores how space might be connected on the larger scales. Topology describes the global structure of space rather than its local curvature. Two shapes can share the same geometry, yet possess different topological structures. A simple example is a flat sheet of paper compared with a cylinder formed by rolling that paper into a tube. Both surfaces are locally flat, but the cylinder connects its edges in a way the sheet does not. Cosmologists therefore ask whether the universe might have a more complex topology than it appears at first glance. One intriguing proposal was explored by the French cosmologist Jean-Pierre Luminet and his collaborators. Luminet suggested that the universe might possess a topology similar to a dodecahedron. A dodecahedron is a three-dimensional shape composed of 12 pentagonal faces. In this model, space would wrap around itself in such a way that travelling far enough in one direction might eventually bring you back to your starting point, much like circumnavigating the surface of Earth. The dodecahedral universe model arose from attempts to explain certain patterns observed in the cosmic microwave background. Luminet and his colleagues proposed that if the universe had this type of topology, light travelling across space could produce repeating patterns in the radiation. These patterns might appear as matched circles across different regions of the sky. Researchers searched carefully for such signatures in data from cosmic microwave background experiments. So far, the evidence for a dodecahedral topology remains inconclusive. While the idea remains intriguing, current observations do not strongly support this particular model. Nevertheless, the possibility of unusual cosmic topology continues to be explored. Other models consider universes shaped like three-dimensional tori, where space wraps around itself in multiple directions, or even more complex structures involving higher dimensional geometry. Understanding the geometry and topology of the universe is not simply an abstract mathematical exercise. The shape of space-time influences how cosmic expansion unfolds over time. It determines whether the universe might expand forever, gradually slow down, or possibly recollapse under gravity in the distant future. Geometry also affects how light travels across the cosmos, shaping the way we observe distant galaxies and interpret astronomical data. In the framework of modern cosmology, these geometric properties are closely tied to the total energy content of the universe. Matter, radiation, dark matter, and dark energy all contribute to the curvature of spacetime. The relationship between energy density and curvature can be expressed through Einstein's gravitational field equations. In simplified language, these equations state that the curvature of spacetime is proportional to the total energy and momentum present within it. This profound connection links the large-scale shape of the universe directly to the matter and energy it contains. Although observations currently suggest that the universe is extremely close to flat, the question of its full topology remains open. The cosmos may be far larger than the observable region accessible to our telescopes. If space extends far beyond what we can see, its global shape could be far more intricate than our current measurements reveal. In this sense, the geometry of the universe remains one of the most elegant mysteries in cosmology. It reminds us that even the shape of space itself is something scientists must discover rather than assume. After more than a century of research, the question of whether the Big Bang Theory accurately describes the origin and evolution of the universe rests on a remarkable foundation of evidence. Unlike many ideas in science that rely on a single line of observation, the Big Bang model is supported by several independent discoveries that all point toward the same general picture. The first of these pillars is the expansion of the universe itself. Observations of distant galaxies show that space is stretching. Light arriving from faraway galaxies displays a shift toward longer wavelengths known as redshift. When astronomers measure this redshift and compare it with distance, they find a clear relationship. Galaxies farther away from us appear to recede more quickly. This pattern is described by Hubble's law, which can be expressed in words as recessional velocity equals the Hubble constant multiplied by distance. The significance of this relationship is profound. It tells us that the universe is not static, it is expanding, and if the universe is expanding today, then in the past it must have been smaller, denser, and hotter. The second major pillar supporting the Big Bang model comes from the formation of the light elements. During the first few minutes of cosmic history, nuclear reactions occurred throughout the hot plasma filling the universe. Protons and neutrons combined to form atomic nuclei such as hydrogen, helium, and small amounts of lithium. Physicists including George Gamow, Ralph Alpher, and Robert Herman calculated how these reactions should unfold under the extreme conditions of the early universe. Their calculations predicted specific ratios of hydrogen and helium that should remain throughout the cosmos. Astronomers have spent decades measuring these elemental abundances in ancient stars and intergalactic gas clouds. Observations from powerful telescopes such as the Keck Observatory in Hawaii and the Very Large Telescope operated by the European Southern Observatory show that the proportions of hydrogen and helium in the universe closely match those early predictions. Roughly 3/4 of ordinary matter consists of hydrogen, while about 1/4 consists of helium. This agreement between theory and observation provides powerful confirmation that the universe once passed through a hot and dense phase capable of producing these elements. The third major pillar comes from the cosmic microwave background. This faint radiation fills the universe and represents light released when the universe cooled enough for electrons and nuclei to form neutral atoms. At that moment, roughly 380,000 years after cosmic expansion began, radiation was able to travel freely through space for the first time. The discovery of this radiation by Arno Penzias and Robert Wilson in the 1960s provided dramatic confirmation of the Big Bang model. Even more detailed measurements from missions such as the Cosmic Background Explorer satellite, the Wilkinson Microwave Anisotropy Probe, and the Planck Space Observatory have mapped tiny temperature variations in this radiation. These fluctuations reveal the earliest density variations that eventually grew into galaxies and galaxy clusters. Together, these three lines of evidence form the core observational framework supporting the Big Bang theory. But the story does not end there. Additional observations strengthen this picture by showing how cosmic structures have evolved over billions of years. Large astronomical surveys map the distribution of galaxies across vast regions of space. These maps reveal an intricate network of clusters and filaments known as the cosmic web. Computer simulations run by research groups at institutions such as the Kavli Institute for Cosmological Physics and the Max Planck Institute for Astrophysics show that these patterns naturally emerge when the universe evolves from the tiny fluctuations observed in the cosmic microwave background. The agreement between simulation and observation provides further confidence that the overall cosmological model captures the essential features of cosmic history. Yet even with this strong foundation, cosmology remains a field filled with active questions. One particularly intriguing puzzle concerns the exact rate at which the universe is expanding today. This issue is known as the Hubble tension. Different methods of measuring the Hubble constant produce slightly different results. One method uses observations of the cosmic microwave background to infer the expansion rate of the early universe. Measurements from the Planck satellite suggest one value for the Hubble constant. Another approach measures distances to nearby galaxies using standard candles, such as Cepheid variable stars and Type 1a supernovae. Astronomers, including Wendy Friedman and Adam Riess, have used these methods to estimate the expansion rate based on observations of the relatively recent universe. Interestingly, these two approaches produce values that differ by several percent. Although the difference may sound small, it is large enough to suggest that something unexpected may be occurring. Some scientists believe this discrepancy could point to new physics beyond the standard cosmological model. Others suspect subtle measurement uncertainties may eventually resolve the tension. For now, the question remains open. At the same time, new telescopes are pushing the boundaries of observation further than ever before. The James Webb Space Telescope, launched by the National Aeronautics and Space Administration, in collaboration with the European Space Agency and the Canadian Space Agency, has begun observing galaxies that formed extremely early in cosmic history. Some of these galaxies appear surprisingly mature despite existing when the universe was only a few 100 million years old. Astronomers are still studying these observations to determine how they fit within the broader picture of cosmic evolution. Every new observation adds another piece to the puzzle. Despite these ongoing mysteries, the Big Bang theory remains the most comprehensive explanation scientists have for the origin and development of the observable universe. It successfully explains the expansion of galaxies, the formation of light elements, the existence of the cosmic microwave background, and the large-scale structure of matter across the cosmos. Perhaps just as importantly, the theory continues to generate testable predictions. That is the hallmark of a powerful scientific idea. At the same time, cosmologists recognize that the Big Bang model is not necessarily the final chapter in our understanding of the universe. Science advances by refining ideas, correcting mistakes, and expanding knowledge as new evidence appears. Future discoveries may modify certain aspects of the model or reveal deeper layers of physical law. For now, however, the Big Bang provides the clearest and most successful framework we have for explaining how the universe evolved from a hot, dense beginning into the immense cosmic landscape we observe today. And in that sense, the answer to the question of whether the Big Bang theory is correct is both simple and nuanced. The evidence strongly supports it, yet the universe still holds many secrets waiting to be discovered.